1.5 Solving cubic and quartic equations. You can generalize the rule for the roots of quadratic equations to any polynomial with real coefficients. Now, if f of z is a polynomial with real coefficients and z1 is a root of f of z equals 0, then z1 star is also a root of f of z equals 0. So if we know one of our roots, z1, then the complex conjugate of that root, z1 star, is also a root of f of z equals 0. We have this important point over here. If z1 is real, then z1 star is equal to z1. Let's take a look at this a little further. Let's suppose that z1, a complex number, is equal to v plus wi. Its complex conjugate, z1 star, that will equal v minus wi. If z1 is a real number, then z1 will equal v plus 0i. Of course, the imaginary part will be 0. And this over here implies that z1 star is equal to v minus 0i. So, what you can see over here, if z1 is real, then z1 is equal to v, and its complex conjugate, z1 star, is also equal to v. So therefore, z1, which is equal to z1 star, is equal to v. And that's assuming that z1 is real. And that's what's mentioned over here. So we can use this property to find roots of cubic and quartic equations with real coefficients. Now, if we take a look at cubic equations for now, an equation of the form az cubed plus bz squared plus cz plus d equals 0 is called a cubic equation. Of course, the highest degree is 3, so we have a cubic equation, and for a cubic equation we have 3 roots. For a cubic equation with real coefficients, either all 3 roots are real, or one root is real and the other 2 roots form a complex conjugate pair. And we have to be a bit careful over here. A real valued cubic equation might have 2 or 3 repeated real roots. And this over here makes a lot of sense. Of course, if we've got one root which is real, then the factorization of the cubic will lead to a linear multiplied by a quadratic, and if we solve that quadratic and get complex roots, those complex roots will form a conjugate pair. For example 10, given that minus 1 is a root of the equation z cubed minus z squared plus 3z plus k equals 0, for part A we have to find the value of k. Now, to do this question, we would have to use the factor theorem. Just as a reminder of what the factor theorem is, if z equals a is a root of f of z equals 0, then z minus a is a factor of f of z. So, we can use this to find out the value of k. So therefore, for part A of the question, if minus 1 is a root to this equation here, first of all we can let f of z equal what's on the left hand side, because we have something equals 0, so therefore f of z is that something, and that's implied over here. So we will first of all let f of z equals z cubed minus z squared plus 3z plus k. And using the factor theorem, f of minus 1, we have minus 1 to the power of 3 minus minus 1 squared plus 3 lots of minus 1 plus k, and this is all equal to 0. So we can use this to find the value of k. We have minus 1 minus 1 minus 3 plus k equals 0. K is equal to 5. And knowing the value of k, we can therefore conclude f of z, that's equal to z cubed minus z squared plus 3z plus 5. And now for part B, we have to find the other two roots of the equation. Well, using the factor theorem, if we know that f of minus 1 is equal to 0, this would imply that z plus 1 is a factor of f of z. We have a linear factor over here, and of course linear multiplied by quadratic gives cubic. So that's stuff you've met during your A-level studies. So for part B, we have z plus 1, our linear factor, multiplied by some quadratic factor az squared plus bz plus c, and this is all equivalent to the cubic over here, z cubed minus z squared plus 3z plus 5. So we can find the values of a, b and c by comparing coefficients. So if we compare coefficients in terms of z cubes, we have z times by az squared gives a z cubed, so the coefficient of z cubed would be a, and on the right hand side we have 1z cubed, so a is equal to 1. If we compare the z squareds, on the left hand side, z times by bz, that gives a z squared, so the coefficient of z squared, that's just b. We've got 1 times by az squared giving us az squared, so the coefficient of z squared is simply a. And on the right hand side we have minus 1 z squared. Knowing that a is equal to 1, b plus 1 is equal to minus 1. Subtracting 1 from both sides, we can see that b is equal to minus 2. If we now compare the number terms, on the left hand side, 1 times by c gives a number term. On the right hand side we have 5, c is equal to 5. And knowing the values of a, b and c, we can therefore conclude that f of z, which is equal to this result over here, that's equal to z plus 1 multiplied by z squared minus 2z plus 5. Now our goal over here is to solve this equation over here. So you'd notice we're solving f of z equals 0. So we have z plus 1 lots of z squared minus 2z plus 5 equals 0. You can see here the first bracket is either equal to 0 or the second bracket is either equal to 0. So we have z plus 1 equals 0, or we have z squared minus 2z plus 5 equals 0. So if we solve this equation and this equation, here you can see z is equal to minus 1, and if we solve this equation over here, we can complete the square. half the coefficient of z, that's minus 1. So we have z minus 1 all squared minus the 1 squared plus 5 equals 0. Z minus 1 all squared is equal to minus 4. Z minus 1, that's equal to plus minus the square root of minus 4. So we have z minus 1 equals plus minus 2i, from which we see z is equal to 1 plus minus 2i. We've got a root of minus 1, we've got another root of 1 plus 2i, and another root of 1 minus 2i. And this result makes complete sense. If we take a look at what was mentioned before, if one root is real and the other two roots form a complex conjugate pair, if we have real coefficients for a, b and c and d for this cubic equation here, you can see here, if we take a look at our solutions of z here, we've got one real root of minus 1, and for the other roots we've got 1 plus minus 2i, which is a complex conjugate pair. So let's just write this down. We have a complex conjugate pair, and that always is the case. If we have a root which is complex, we can determine the other root simply by finding the complex conjugate of that complex number. And from this, if we take a look at what was mentioned over here, we can factorize our cubic as the product of three brackets. And of course, in this particular case, what we saw in section 1.4, when we have z minus alpha lots of z minus beta equals 0, either z is equal to alpha or z is equal to beta. Either the first bracket equals 0 or the second bracket is equal to 0. So knowing the roots, we can write our result using the product of brackets equals 0. So what we mean by that is we have z minus 1 multiplied by z minus 1 plus 2i multiplied by z minus 1 minus 2i equals 0. So this is an alternative way of writing our cubic equation. Either this bracket is equal to 0, in which case z is equal to minus 1. Either this bracket is equal to 0, in which case z is equal to 1 plus 2i, or this bracket is equal to 0, in which case z is equal to 1 minus 2i. So therefore, if we tidy this up a slight more, we have z plus 1 because we have minus and a minus which give a plus, and then the other two brackets remain as they are. So here we've got z minus, and then in brackets 1 plus 2i multiplied by z minus 1 minus 2i. And all of this is equal to 0. So this over here is our cubic equation, which we have just factorized as the product of three linear brackets. The reason we have three linear brackets is because a cubic has three roots. Of course, on our calculator we can confirm whether our results are correct or not. We go to the equation solver. We have a polynomial of degree 3. We type in our coefficients. We have 1z cubed minus 1z squared plus 3z plus 5, and all of this is equal to 0. So indeed, you can see here we get a solution of minus 1. We get another solution of 1 plus 2i and another solution of 1 minus 2i. Now, an equation of the form az to the 4 plus bz cubed plus cz squared plus dz plus e equals 0 is called a quartic equation and has 4 roots. So because the highest order is 4, we have a quartic equation, and because of that we've got 4 roots. Now, for a quartic equation with real coefficients, either all 4 roots are real, 2 roots are real, and the other 2 roots form a complex conjugate pair, or 2 roots form a complex conjugate pair and the other 2 roots also form a complex conjugate pair. And we need to be a bit careful. A real valued quartic equation might have repeated real roots or repeated complex roots. So let's take a look at a couple of examples to illustrate this. Example number 11. Given that 3 plus I is the root of the quartic equation 2z to the 4 minus 3z cubed minus 39z squared plus 120z minus 50 equals 0, we have to solve the equation completely. So the first thing we can do is recognize we have something equals 0, so we can let that something be f of z. So first thing we will do is we will let f of z equal what's on this left hand side over here, which is 2z to the 4 minus 3z cubed minus 39z squared plus 120z minus 50. Now, we know already 3 plus I is a root of f of z equals 0. So, our first root, we'll call this z1, that's equal to 3 plus I. And we know that if we have a complex root, we can determine the other complex root by finding the complex conjugate of 3 plus I. So therefore, z2, that's equal to 3 minus I. So with this, we can form a quadratic which will be a factor of f of z. So what we can see from here then is these two can help form a quadratic factor. So we have here z minus 3 plus I multiplied by z minus 3 minus I. So this over here is a factor of f of z. So we can expand and simplify all of this, and as we did before, instead of multiplying each of these terms together, we can rewrite this as a difference of 2 squares. So here we've got z minus 3, so that's the z minus this 3, and then minus the I multiplied by z minus 3, and then the minus and the minus, that gives a plus. So here we've got the plus I. So now we just need to simplify all of this over here. So if we do that, we have over here z minus 3 lots of z minus 3, so that's z minus 3 all squared, and then we have minus I times by positive I, that's minus I squared. So we have over here z minus 3 multiplied by z minus 3 minus I squared, so we subtract off minus 1. Of course, I squared, that's the same as minus 1. So we've got z squared minus 6z plus 9 plus 1. So simplifying this, we've got z squared minus 6z plus 10. This is a quadratic factor of f of z. So let's just write this down. Here we've got a quadratic factor of f of z. With this we can form another quadratic factor, recognizing that z squared minus 6z plus 10 multiplied by az squared plus bz plus c gives this quartic polynomial 2z to the 4 minus 3z cubed minus 39z squared plus 120z minus 50. And with this we can compare coefficients to find the values of a, b and c. So we will now compare coefficients. So if we do that, comparing the z to the 4s, on the left hand side, z squared times by az squared gives az to the 4, so the coefficient of z to the 4 will be a. And on the right hand side, we've got two of them. We can see here a is equal to 2. If we now consider the z cubed terms, on the left hand side, z squared times by bz, that gives a z cubed, so the coefficient there is b. Then we have minus 6z times by az squared, that gives a z cubed term, so the coefficient will be minus 6a. And what else we know is on the right hand side we have minus 3z cubed, so the coefficient of z cubed is minus 3. Knowing that a is equal to 2, we have b minus 6 times by 2, which is 12. This is equal to minus 3, so we've got b minus 12 equals minus 3, and therefore b, that's equal to 9. Okay. And knowing that b is equal to 9, we can find the value of c by comparing the number terms. So if we compare the number terms, here we've got 10 times by c on the left hand side. On the right hand side we've got minus 50. C is equal to minus 5. Knowing the values of a, b and c, we can therefore conclude f of z, that's equal to z squared minus 6z plus 10 multiplied by 2z squared plus 9z minus 5. And now we need to solve f of z equals 0. So here we've got z squared minus 6z plus 10 multiplied by 2z squared plus 9z minus 5 equals 0. So if we solve over here for z, we know from here we get solutions of 3 plus I and 3 minus I. So from here we know that z is equal to 3 plus minus I, and if we solve this equation, 2z squared plus 9z minus 5 equals 0, we can factorize this as 2z minus 1 lots of z plus 5 equals 0, from which we can see z is equal to 1/2 or minus 5. So therefore we can state the roots to our original equation. We can therefore see that z1, that's equal to 3 plus I, z2, that's equal to 3 minus I, z3, that's equal to 1/2, and z4, that's equal to minus 5. Of course, with our calculator, we can confirm these results over here. So if we take a look at our equation on our calculator, we simply go to the equation solver. We have a polynomial of degree 4. We enter in our coefficients. We have 2z to the 4 minus 3z cubed minus 39z squared plus 120z minus 50, and this is all equal to 0. So you can see here, indeed, we get a solution of 1/2, we get another solution of minus 5, we get another solution of 3 plus I, and another solution of 3 minus I. Example number 12. We have to show that z squared plus 4 is a factor of z to the 4 minus 2z cubed plus 21z squared minus 8z plus 68, and hence solve the equation z to the 4 minus 2z cubed plus 21z squared minus 8z plus 68 equals 0. Well, it's not as straightforward as using the factor theorem over here. But what we can do instead is use algebraic long division, and if we get a remainder of 0, we can therefore conclude z squared plus 4 is a factor of this result over here. So, using long division, we first of all, with long division, write down the z squared plus 4, and we then write down the z to the 4 minus 2z cubed plus 21z squared minus 8z plus 68, and we put this in some sort of a bus stop, as shown here. And then we think to ourselves, z squared times something gives z to the 4. What is that something? Well, of course, that will just be z squared. Then we multiply z squared by this result here. So z squared times by z squared, that's z to the 4. Z squared times by 4, that's 4z squared. And I'm going to write this under here. So here we've got 4z squared. And then we simply subtract these. And if we subtract these, z to the 4 minus z to the 4, that's 0. Then we've got this minus 2z cubed, take away 0 essentially, that will be minus 2z cubed. Then we have 21z squared minus 4z squared, that will be 17z squared. And then these two terms drop down with it. So here we have minus 8z plus 68. We then think to ourselves, z squared times by something gives minus 2z cubed. What's that something? Well, that will be minus 2z. And then we multiply this minus 2z by this result here. Minus 2z times by z squared, that will be minus 2z cubed. Minus 2z times by 4, that will be minus 8z. So, we then subtract these results. So, minus 2z cubed minus 2z cubed, that's 0z cubed. 17z squared minus 0, that will be 17z squared. Minus 8z minus 8z, that's 0z. And then we take this 68 over here. We then think to ourselves, z squared times by something gives 17z squared. What's that something? Well, of course, that's just plus 17. And then we multiply this 17 by z squared plus 4. 17 times by z squared, that will be 17z squared. 17 times by 4, that's 68. And then we subtract these results, and doing so, 17z squared minus 17z squared, that's 0z squared, and then the 68 minus the 68, that's 0. Indeed, we get a remainder of 0. So let's just write this down. Because we get a remainder of 0, we can therefore conclude z squared plus 4 is a factor of z to the 4 minus 2z cubed plus 21z squared minus 8z plus 68. And what we can now do is recognize here we've got a quadratic factor. Here we've got something to the power of 4. So therefore, we can factorize this polynomial as the product of two quadratic factors. And if we do that, we have z squared plus 4 multiplied by some quadratic. Now this quadratic is this result over here. Z squared minus 2z plus 17. This is all equivalent to z to the 4 minus 2z cubed plus 21z squared minus 8z plus 68. And now our goal is to solve this side equal to 0. So in other words, we've got z squared plus 4 multiplied by z squared minus 2z plus 17 equals 0. So either the first bracket equals 0 or the second bracket equals 0. So here we have z squared plus 4 equals 0, and here we have z squared minus 2z plus 17 equals 0. So now if we solve, you can see here z squared, that's equal to minus 4. So z, that's going to equal plus minus the square root of minus 4. In other words, z equals plus minus 2i. And if we solve this equation, we can complete the square. So we've got z minus 1 all squared minus 1 squared plus 17 equals 0. Solving this, z minus 1 all squared plus 16 is equal to 0. Z minus 1 all squared is equal to minus 16. Square rooting both sides. Z minus 1, that's equal to plus minus the square root of minus 16. So you can see here z minus 1 is equal to plus minus 4i, and taking this 1 to the other side, you can see z is equal to 1 plus minus 4i. So we've got 4 roots over here, and that makes sense because we've got a polynomial of degree 4 which we're solving. So we can conclude here z1, that's equal to 2i, z2, that's equal to minus 2i, Z3, that's equal to 1 plus 4i. Z4, that's equal to 1 minus 4i. And what you can see over here, we've got two complex conjugate pairs. So here we have a conjugate pair. Here we also have a conjugate pair. So therefore these are our results, and if we go to our calculator we can use the equation / function menu to solve this. We have a polynomial of degree 4. We simply type in our polynomial, so we have 1z to the 4 minus 2z cubed plus 21z squared minus 8z plus 68. It turns out we get 1 plus 4i, which is what we have over here, 1 minus 4i, which is what we have over here, 2i, which is what we have over here, minus 2i, which is what we have over here. So we can use our calculator to check our answers.